Good afternoon. Just to let you know, I put up on our webpage, I put up a page that is called Photo Gallery, and I'm hoping you can send me your nice pictures so I can put in there. If you have nice pictures from the conference, please send me and I'll put on the webpage, okay? The chair of the session is you.
Hello everybody, it's time to start our afternoon sessions and let's welcome Albert from Lisbon. He will give us a talk on outsider's perspective of Steptoe and his libraries.
Thank you. Thank you. So this is a good start, so because this talk should be a little bit lighter than the other talks of this conference. But I'm trying to show you a little bit about different things, especially about signal processing and different areas and different applications of signal processing. So I thank you a lot for the Paula and Ismaila for the invitation. Okay, so before start, it's working. Okay, first things first, as usual. I think it's very important to define what we're talking about. So, to give names to things, right? So, because a name it represents what we're talking about. And this all started probably with Saint Augustine. Saint Augustine, he created this idea that the name is directly connected to the thing itself. And then it came Bertrand Russell, who gave this idea that the name is not the thing itself, but the name defines the thing. So it defines structural relations that the thing has. Okay? And so the name is related to two propositions about something. And this all ended up now in the modern times with Jacques Derrida. And it's so a mess because a name can mean anything it all depends on the context that you are using that name. Okay. So, and this is something, when you talk about spectra, it depends also on the context that what we are talking about, right? Because you can talk about the spectra, that's the spectra from a star, a spectra from a music, from sound, a spectra from a graph, but also different things. But in the end, they represent things that are similar, right? Okay, but what do we talk about then when we talk about spectra and its libraries? So spectra first. So the spectra from if you search in the Oxford English Dictionary, the second edition, well, the first thing that comes is that spectra are ghosts. So spectrum, and spectrum, it's a phantom. And this is important because a phantom is in fact an image or a semblance of something. Sorry? Okay, but I searched in spectrum only, but okay. Then the next definition that comes in the dictionary is that the spectrum is an actual or notational arrangement of component parts of something that are arrangement of some phenomenon that is arranged organized according some frequency, energy, mass. So this is much more the spectrum that we work on. Right? And there is something that's really important here is that at the same time that the spectrum can be a semblance of something or an image of something, it also presupposes that this something can be decomposed. That you can decompose a phenomenon and still keep an image of this phenomenon that is decomposed. And this is an assumption because this might not hold true for all things that we study. But this is an important assumption that we need to simplify later in order to try to understand it. Okay, so these are just some examples of spectra, but the important thing here is that the spectra we can use the spectra as the underlying signature of things. Okay, but what about libraries? So also according to the OED, so libraries are places set apart to contain books for reading and study of reference. And there is a comment that's really important, that this cannot be applied to a shop or a warehouse of a bookseller. So those are two different things. Right? And there is also another definition that says that it's not only that you set apart things, but that also you need to share those things in some way. Even if you charge to share things, you can charge, but you need to share. And I think the important words here are that a place to set apart, containing a collection for the use, and I forgot this one, charging with the care. So it's not only that you select a set of spectra, put them aside, and it's there. You should also take care of that. So the notion of long-term preservation is inside what a library is, and lending to other people to use. So in a certain way, if you could write one phrase to sum up those definitions, basically libraries are curated long-term collections of some type of knowledge that can be contributed to derive further knowledge. So a library is not a place that dies. It's a place that's there for us to use and to derive new knowledge. And for those who are going to stay here in São Paulo, this very nice library, it's at the University of São Paulo. It's really nice to visit. It's a beautiful building. Okay, but now a little bit about the value of spectra in its libraries, right? Because spectra libraries, especially libraries, they are only as good as they can help us to either understand or to emulate the underlying things that they are representing. So they don't have a value on themselves. They have the value of helping us understand the nature. And in order to do so, in order to understand the nature, we need to follow some processes. One of the processes is the analysis. And the other process is the synthesis. And basically, analysis, it's breaking up. So when you take the spectra or you take anything that you are studying, and you try to decompose in exactly those parts that you assumed that it was an assumption, an early assumption that it was possible to do. And this is something that is really an assumption. And the other processes, that is the synthesis. So it basically means that you combine things, smaller things, to create something new or something bigger. And we need to use those processes because in the end what we want is, that this machine could work, is that the thing, so it's something in the nature that we want to understand. And we want to understand, so we want to grasp with our heads something that's outside of our heads. And we need to pass through a process to arrive there. And this process is highly indirect. It's not direct. And so you have the observational process that changes about the nature of the thing. And then this will arrive in some data. This data will be processed again, and will generate more data. And then we will try to do some early analysis to arrive at some type of parameters. And then we will try to synthesize, so we will interpret those parameters, and we will try to synthesize using those parameters. Sorry. So we are trying to synthesize using those parameters more data, and we are going to look through the system during generations before actually being able to perform some type of analysis on the parameters, some type of inference on the parameters that will allow us to perhaps create an image of the scene in a way that we can understand. So this is more or less the process, and this is the importance of why we are using libraries, why we're creating libraries, and why we're using them. It's to allow this analysis and synthesis process to happen. Okay, so now just a little bit about synthesis. I'm not going to talk a lot about synthesis, because synthesis is really a very domain-specific process. So the synthesis process depends on what you are trying to synthesize. So all the physics laws, all the pre-existent a priori information about the data that you have needs to be inside the synthesis, but this is really domain specific. We have been seeing here in the conference several talks that mentioned synthesis process and how we synthesize spectra from parameters. And this synthesis basically can be either synthesis that is going to use some data entering the system or not. But most of the time, if you are using data, even a theoretical spectra is using data from lines. So it's very hard to have a real 100% theoretical spectrum. But basically, the basic idea of the synthesis of the process is that you can write, here in this specific case of the SSPs, you can write a function that you will have stars and of certain masses, and a certain number of stars of certain masses. And this equation, that in fact should be a sum and not an integral, because stars are finite, this is not a continuous process. This equation makes an important assumption that actually you can create something from a linear combination of things. Right? We're just adding the stars. Well, I think that Igor already showed the process earlier during this conference, but basically from the IMF, that's not the International Monetary Fund, that basically tells us how much mass you have for certain size. And the isotopes, and from a library of spectra, you can use as one SSP. And then you use again those SSPs to compose with this and a history of evolution to compose the spectra of composite population, composite cell population. Okay, but this, in both cases, you are assuming that you can do this, that you can just add things, and that the process is entirely linear. So this is basically the strong hidden assumption on all this process. And this is also valid, it's not valid only for us. This is also the way that the voices in the train stations in France, for instance, they work. When you go to a train in SNCF, the woman that is speaking is not a woman, it's actually a computer that synthesizes the voice. And it's this concatenative process where you just get the phonemes and add them, or it's what they call the formal speech synthesis. And this is what you have in all your GPSs. So this, you don't have a library. You don't have a library of phonemes. What you have here, it's 3 to 5 phonemes that are morphed and transformed into all the other phonemes that we can do. Basically, these formal speech synthesis systems, they are very simplified. They try to synthesize things. But this is not valid for the most modern speech synthesizers. The most modern speech synthesizers, as well as the most modern digital pianos, they actually try to simulate the entire process of the production of the sound from basic principles. I think this is really interesting how this works. But now something that will be perhaps more of use for us is the analysis process, because the analysis process it's not domain dependent. It's much more independent in terms of the application that you're doing. Okay. So as we saw earlier, also during this conference, the analysis process can be empirical. So if it's empirical, it is just based on specific features that you measure, and then you have a calibration between these features and some property of what you're studying. And one example was Milani's presentation. And another way is to do an empirical, but it's still based on the synthesis of empirical building blocks, so those SSPs. Basically, you require previous building block libraries, and those can be spectral phonemes, instruments, lights, stars, and you also need a synthesis code, like it was mentioned here by Warley, the Matisse code. This is really nice by the back. And Rodolfo and okay. And as we were saying, you have to make this supposition of linearity. In one case and in the other case, that all the relevant parameters are being measured. So if you are performing a calibration between a line ratio and some property, you need to assume that there is no other property that can arise in your object that will change the property that you want to impute. Okay, and then there is the theoretical approach. And well, I just note here that there are many people trying or starting to work with Bayesian approaches to do SST modeling. Like Metier commented on that, Garcia, Rodolfo commented many different methods. And perhaps later we'll have also a presentation by okay. So either the empirical or the theoretical approaches need some type of underlying assumption on how to compare your data with what you are synthesizing. And actually, it doesn't matter if you have a perfectly good code to synthesize things. You also need to have the right way to compare what you're synthesizing with the data. And this is not as easy as we usually assume, because basically, how we compare? We compute a distance between two things. And to compute a distance, we will use a norm. And norms are generic. Usually we just put the 2 here. So usually we just use the what's called the Euclidean norm, or the L2 norm. This is the Euclidean distance. And in this conference, I think that everybody used only the L2. But there was no mention about the L1 norm or the L0 norms. But L2 is not the panacea of the world. And the nice thing, the interesting thing, is that, well, first thing, contrary to certain popular beliefs, that the L2 norm does not necessarily result in the optimal solution. Right? This is important. And why? For the same reason that makes working with L2 norm, with the L2 norm simple. That is smooth. You can compute the derivatives. And then you can just walk through the derivatives and arrive in an optimal. And because of this property, it does not guarantee the optimal solution. But for many problems, if you know that your problem has one single optimal, then you are safe. No problem, you can use that too. But if you don't know, you should first study the region where you are trying to optimize, because otherwise you can easily arrive in very local optimal. Okay? The next best thing, and today in the signal processing world, people is really working not with the L2, but with the L1 norm, or the L1, or the L2 plus L1. The best norm possible in science would be what we call the L0 norm. The L0 norm, what is the L0 norm? The L0 norm is just counting how many different things, for instance, in your vector are different from 0. What you want when you're comparing what you're synthesizing with what you observed is that everything is zero, right? But obviously, this is in the presence of noise, this is completely impossible. And also, there is another reason why people don't work with the L0 norm, is that if the optimization of the L0 is an NP-hard problem, and for those who are not aware of computer science, an NP-hard problem, it's worse than a singularity for us. So when you see an NP-hard problem, you burn, like you have seen that. Or you try to solve them with the price. Okay? So you usually avoid to work with L0 unless you know how to solve the problem beforehand. Usually you work with L1. And the nice thing of L1 is that it also promotes sparsity. So if you have complex things, you have many complex things, you would rather to choose from your library the less complex things that you could, the less complex explanation that you put for your data. So, and then this is what the L1 norm does. The L0 does perfectly, the L1 is an approximation. The problem with L1 is that it forces you to search, brute force search from solutions. Because you don't have the derivatives, you cannot climb, you cannot walk through your parameter space. You can just try to explore it. There are many studies in the field of complex optimization. And today there are many libraries available to work with L1, and most of them are in MATLAB or in C. But people from signal processing they work really a lot in MATLAB. Okay, and this working with this norm opens a new possibility in science that's called compressed sensing. That if I have time, I will comment a little bit about it. But anyway, everything that I'm commenting here about the L1 norm is really recent because many mathematical theorems that allows us to work with this norm appeared after 2006. So, and this is still in the math world. So we are going to the math world to try to take things to bring to science. And what created an explosion of studies about the L1 norm is this word compressed sensing. What is compressed sensing? Compressed sensing, it's the concept that you can reconstruct perfectly a signal that is sparse in some basis from very few measurements. But you need to know that the signal is sparse. So if you have a signal that you can project into, for instance, a wavelet basis, then you can just try to measure the wavelet coefficients. Right? You don't need to measure the entire signal. And then you have much fewer measurements than normally you will need to derive your data. So basically, this is just mathematical representation. So if you have any measurements, and if your signal is sparse in some basis, you can just project it and arrive back and reconstruct basically your signal. I'm going to show one example here that is from a paper by Taylor et al. In the IWSSL transactions on computer graphics. So he was very interested in astronomy. Now, if I'm not mistaken, he's working in SPA with the reconstruction of data from SPA. But he's a computer scientist. So basically, this is the data. So probably most of you will recognize those data from the Hubble archive. It's just 2 images from the Hubble archive, from the Hubble Heritage. And when you try to reconstruct these objects in 3D, so I use this as I want to have one object in 3 dimensions to which the annual norm, an optimization of the annual norm of the projection of this object will be similar to this or to this. And basically, this is the reconstruction that he managed to do. And this is the nebula, so this is exactly in the same projection, but this is the reconstruction. This is the data. This is the data, and this is the reconstruction. And here are other points of view of this data set. But the reconstruction seems perfect, right? But there is no physics inside it. But there is no physics inside it because he was a computer scientist. Because there is nothing preventing anyone to use exactly the same approach, but with physical constraints about how transfer works, right? And you can perhaps try to reconstruct in 3D entire objects with a real physical approach. So this is just another example of a reconstruction for the Cat's Eye Nebula. And here's the data, and here's the Cat's Eye Nebula seen from different perspectives. Okay, again, it's the same problem. The overall structure seems fine, but where are the physics? We don't know what's correct or not. Yet, this is another example that I wanted to show you, but now it's about something that it's a mixture between empirical and theoretical optimization analysis, and it's the separation of sounds in a recording, but it's in an almost completely blind way. So the only non-blind thing that you do is that you assume that you can model features, spectral features, using Gaussians. Yep. Okay. So basically, this is the sound of a xylophone. So the process basically that will happen. This is a matrix just with the sound of a xylophone. And then so it's basically frequency, time, and amplitude in Z. So the color is the amplitude. You could imagine that this is not a xylophone, but this could be an IFU data, right? But so let's imagine that this is just a xylophone. That's what they did. So what they did is to construct to decompose the spectral power distribution of the sound in different bases and components in an almost blind way. The only thing that you do is that you constrain that the spectral features, so the modeling of Gaussians in one xylophone recording, will be more or less similar to the modeling of Gaussians in all xylophone recordings. So this is just the non-blind part of the process. So this is the sound, and now the sound. I will play the song again because I pressed back. But so now I will show you how the computer alone, without any further assumption, but this assumption that you can model with Dolphins, and that you had a basis for learning how some different instruments would see in a Gaussian decomposition, how he managed to decouple in 3 different voices. So this is the first voice that he found. The second.
I want to touch you.
And the third. And he did this in a completely blind way. And it's really amazing that today we can do those things with sound. And the reason why this is possible is because there is also a correlation in time. So of the frequency is not just localized, so it's not like one spectrum that you take, but it's like a knife view if you just change time, force, or position, right, for space. So adding constraints regarding time or space can probably help us a lot in the analysis of spectrum. Okay, in blind analysis of spectrum. Okay, now I will show some examples of a fully data-driven, and the data-driven now it's really human blind. So now there are not even Gaussians being put inside the model. But those types of human blind, completely human blind, requires us to pose questions to the data much more carefully, because well, basically an algorithm will process the data and will give you something. The algorithm does not know what it's doing, and the interpretation of the results, it's sometimes rather tricky also. So the first, this is an area that's really in its infancy. So I think that probably there was no application in astronomy before 10 years ago, or 11 years ago. So one is what we call smooth CA. So basically it's an independent component analysis, and this is rather old, but assuming that the signals are smooth in some way. And this was applied to Raman spectroscopy to try to identify different components of a mixture. So these are 3 different mixtures. So this is 2 different mixtures. And you assume that the pixel is smooth, but you don't assume how they are. Just that they are smooth, for instance, they could be a point profile, but you don't assume any form for them. And also you assume that they are positive, but if they're negative, then it doesn't apply by default. When you apply smooth CA to this 3 spectra, you get these 3 decompositions. So, and these 3 decompositions, so this gray line is the true spectra for the polyethylene. And this black line is what the smooth CA recovered from here. So you're not teaching how polyethylene seems. It's covered by itself that in these 3 mixtures you could decompose in 3 different spectra. And that's the 3 different spectra. When you go to the spectral library and you try to identify, you find the matches with chemical components. I don't know about you, but to me this thing is really amazing that a computer can do this completely by itself. And everything that I'm showing is, I think that now it's everything after 2011 or 2012. Okay. So, as I was saying, that the spectrum is not perfect, the reconstruction is not perfect, but it's good enough for you to identify in the spectral library what's the component, what's the chemical component. Okay, another example that I'm going to give, it's a more personal example. It's about a heuristic method that I created a few years ago to disentangle cluster and few stars, but also in a completely human blind way. Okay, when you are trying to disentangle a cluster from few stars, what are the most what are the weakest assumptions that you can do about cluster and few stars? Or if you don't want to impose a model on what a cluster should look like. So basically, that member stars of the cluster should be somehow located in the same region of the space, right? And that they should also share some common characteristics. I don't care about what are the characteristics. In fact, I don't want to force the machine to use some characteristics. I'm just saying that there are some characteristics that should be similar between them. So if we try to translate this into a code, and because you cannot ask this for a machine, so you should ask something more like that, So cluster stars may be clustered in many parameter spaces, in many different parameter spaces that you don't define what are the parameter spaces. And the few stars may be clusters in some parameter spaces, but they are going to, when you change the parameter space, they're not going to cluster, and things will be more or less random. So we implemented a method that uses different algorithms, and it actually works quite well. So this is just an example of a field with a cluster. So this is the simulation. Now it's a simulation. This is a field plus a cluster. So this is just a simulated cluster that is here inside. And sorry for the accent is different from this one. And this is what the method recovers in a completely blind way. So the size of the dots indicates the membership probability. It's completely blind. We never thought that a cluster should have this term, right? And the methods managed to find parameter spaces that all the stars were always clustered. And of course, this also works for real data. So this is a small field, a cluster. When we applied up mask to this object, this is a young cluster. It has 10 megayears. It found by itself the sequence. It found by itself double stars. We never thought that to the machine there are double stars to look for. And he also found perhaps what we think that is an indication of a PMS. And since the cluster has 10 megayears, the PMS should be around more or less around there. It's quite interesting that a machine can do that also by itself. Okay, another example. I invite you to visit my poster that it's outside. It's completely data-driven methods that was used to create emission line galaxy notification. And it's really, really interesting because this method, in a completely blind way, managed to recover all the classes that we know from the BPT and from the one diagram. It's not exactly the same classes, but they are very similar. So this is quite interesting. And during this meeting, we have been seeing also a data-driven method that's called the TSNE, that have been used by during presentations by Sina, by Peter, and by Paul. Okay, and I think that now one example that is rather interesting for people working with spectra is this of unmixing data cubes, but now of real spectra, not sound spectra, not Raman spectroscopy, a real spectrography, but not an astronomical spectrography, because there are no astronomers using this yet. Okay, first how it works. Basically, do you remember the norms? So we need to optimize some distance. And what we are going to optimize here is a distance that is a mixture between an L2 norm and an L1 norm. So what we do is we write the L2 norm to give you the data fidelity term and an L1 penalty. So if you have many components, this G will increase and then you are not going to be minimizing them. So it's very, if you have two explanations for your data, but one explanation has less components or in a certain way needs less stars or a smaller dictionary of stars, then you prefer this more compact representation of it. Okay, so basically this X is the pixels, so pixels in the large sense. So what we do here is a dictionary, so this can be your spectral library, for instance. Or in this case, it's nothing. It's not a library. It's just a random selection of values. But it could be your spectral library. And then you have the coefficients for the representation. And then you have the coefficients for the representation and the regularization for the detail. I will jump to the algorithm. So this is the data. So this image is an Earth observation satellite with an IFU, equivalent of an IFU. And this is the data of the IFU, but if you take the stripe and just represent pixel by the value of the spectrum, you'll see the representation. And so these are the two spectra, and these are the decompositions that it's doing. When you try to compare the decomposition that the machine did by itself, you start recognizing sand and different spines, and even moods, patterns, water, a submerged net even, and you manage to recognize the different components of the data. And so the blue line is the example spectrum. So this is the real data, and the dotted red line, it's what the machine managed to discover by itself. So it's still different. Probably the errors will be much more than 0.2. But you can imagine what we will be able to do with this type of methods 20 years from now. So these methods are extremely new. I think that this method has less than 5 years, less than 8 years old. The application was less than 5 years. And this is basically what Peter was saying, that science in a certain way is changing. The way we do science is changing. So from the empirical, historical way to do science, the theoretical branch that started to write analytical equations. And then the analytical equations were not enough anymore. And then we started to write computer software to try to reproduce the reality. Now, what we are trying to do, it's actually to integrate all those things. And actually, from the data, generate simulations that generate data that are compared to observational data. So it's a cycle that closes. Okay. There is all this new data-driven work requires that we have some prior knowledge, and this prior knowledge of the work comes from the libraries that we're defining. And the important word also curated, not only defining. And a library is only as useful as the information it contains, as we have been seeing in different presentations during this meeting. And there is one interesting phrase by Tycho Brahe that he wrote when he was 17, and that in his vision there are just as many measurements and methods as there are astronomers, and all of them disagreed. And this was almost 500 years ago. And this is a picture that's changed very, very little. Right. Well, in his vision, what was needed was a long-term project with the aim of mapping the heavens from a single location over a period of several years. But what I think that's really important is this long-term projects. We should try always to aim for very, very long-term things, and not just for, okay, I wrote a paper and then it's over, I will never look to this anymore. And I think that one should really always make an effort to keep as much overlap as possible. For instance, with libraries, we should always try to keep an overlap, like Pelletier was saying, because with this overlap, you can always calibrate from your previous knowledge to your new knowledge. You should never lose the connection between the old science and the new science. And this capability to connect old results and new results, it's more important than just calibrating things. Because it's because of this that we can, for instance, have very long-term studies that we cannot foresee. When the oceanographic catalog and the Carduchiel were created in the beginning of the last century, we were not thinking that the Hipparcos satellite would fly almost 100 years later. And then with the Hipparcos satellite and the oceanographic catalog, we created the Tycho 2 catalog. The Tycho 2 catalog that most of us use only exists because some people 100 years ago considered that it was important to keep knowledge for long term. So the preservation of data heritage and the scientific long-term data heritage, it's of utmost importance. I think that perhaps Elizabeth has comments a little bit about it later. I don't know. Okay, so another thing that's also important for a library is how easy it is to extract information from the library. So it's a library that's so big that you cannot go inside the library and extract things. It's an useless library. You need to be able to go to the library and extract information. And this is what I will talk a little bit about now. So it's about retrieving information from libraries. Okay, so usually, how do we retrieve information from spectral libraries, or from any libraries in a certain way? It's usually using metadata, right? I think that Igor showed the IWSSL website, and here you can search for any type of metadata, entering limits and parameters. Can you use ADQL?
Yes, not in this format. You can use quite complex versions, just very simple. You can use ADQL.
Okay, so basically, this metadata is the parameters that are obtained from the individual spectra analysis when you run the analysis, or that were used to synthesize your spectra. And then you're just going to add this into a database, and then just run queries in SQL or simple queries over the database. So this is the most standard way to do to search a library. But there are other ways also. One way is by similarity. So you need to have a similarity concept. And in the specific case of spectra, the similarity must guarantee that low resolution spectra should be similar to high resolution spectra, except in terms of resolution. But they are representing the exact, the same abstract entity. So they should contain up to a certain resolution the same information, more or less the same information. And usually what people do is to convolve the high resolution with a filter and then just degrade information. But actually you don't need to do that. One thing that can be done is to find a common multi-scale transformation of your data that guarantees that the high resolution and the low resolution spectra, up to a certain scale, will have the same coefficients, or at least similar coefficients. And actually, this is very interesting because if you can do that, you can also do another very interesting thing, is that this can allow something that's called super resolution to be performed. So this is a paper, this is a results by paper by Fadili et al. That was published in 2009, the Computer Journal. And basically, this is the real data. So just assume that this is your low resolution data, just to scale to have the pixels more or less at the same time. Right? If you decompose this data into a certain basis, that is a wave, that is spatial wave of basis, and you try to reconstruct from this decomposition a higher resolution version of this image, you get this reconstruction. So basically, this is the reconstruction. So this is the real, this is the reconstructed from this. Obviously, you should not do science here, because the pixels of this image, they are extremely correlated. They are correlated everywhere. The noise is, if you just create an histogram of the noise, you see a horrible pattern. But for indexing and searching, it's really amazing. Okay, so if a spectra can be decomposed in this way that I was showing, you can index directly your library using those decompositions, and then you can search your library using this decomposition. And this is interesting because this opens possibilities that you can just get your spectra, upload to a page, and then it will return you all the similar spectra from the library. And this is more or less, it's not exactly this because Google is using deep learning, but this is more or less what Google images do. So I took a picture of Sparkle's meeting in '88, and I just dropped it to Google. And then Google returned a meeting, well, with, it's similar. They're not scientists, but it's similar at least. You're not athletic. Can you do something similar for spectrum? Would it be useful? I think it would be useful anyway, but perhaps. One thing that is important to notice is that we have already something like this for astrometry. So there is this site that was created by Dustin Lang some years ago that's called astrometry.net. So if you're lazy to do your astrometric calibration of your image, and if you just need something that's very rough, you just upload your image to astrometry.net, and it will index the image. It will create quads between the stars, and it will search among Tycho and probably now Gaia also, and we will put your WCS in a standard compliant way. So we have been talking about many different things, but where are the gaps that, well, I just created an abstract with a few gaps that probably were commented during this meeting, and that were commented during this meeting, and a few more that I imagined. So the first one is that the theoretical versus empirical question, where we have incomplete lists versus remote samples. The second one is that you have several libraries visible, but very few in near infrared and UV. Okay. The third one is this question about how to live between two worlds, high res versus low res. I think that this is a question, that perhaps we could solve using smarter methods, so just algorithms. The other one is the variant evidence patterns that are needed, and also specific stars that are missing from general spectral libraries. Another one is the degeneracies in the analysis, and the needs of external data to break this degeneracy. One example was anthropology from astroseismology. And this is something that I am adding. Also, perhaps there is a need to better pose the problems, right? And also, basically, when we're trying to solve problems as astronomers, we don't try to formulate them in a way that they are going to become well-posed problems. We try to solve ill-posed problems by force in many cases, and this is not very helpful. Okay, another one is that I think that this will be the discussion after there are two talks afterwards. What's in the coffee break? And that we need to develop spectral libraries and to link them directly with surveys and with the needs of the surveys. There were several discussions about the need of better modeling of binary stars and about multiple stars. And something that I wanted to add is that where are the error bars? Because there are many things that we just don't have error bars. And it's not, because you can, formal errors, you can always add. There's no excuse. Systematic, perhaps not as harder, but formal errors, you can always add. Another thing that we didn't comment yet here is the technique, because today there are many different technologies. For instance, CPUs and FPGAs that can perhaps, I don't know if this is true, but make this storage with certain interpolation that is used in some approaches for synthesis more resource expensive than just processing on the fly when you need. I don't know how long does it take to compute, to synthesize the spectra from lines. I was commenting with Bruno yesterday, it was something like some minutes perhaps. But if you can run it at 1,000 times faster, perhaps you don't need to store the library. You just have the library of lines, at least for 1D, and your synthesis, and then you synthesize on the fly. Okay, another thing is that how to take into account the source variability, because sources are variable. And we saw this morning a discussion with the line that appears in the works. So the spectral libraries, they don't contain those sources with varieties. Or should we add them, perhaps? And the other thing that was a little bit commented this morning with Manga is that the spatial information is an additional constraint. So we should start worrying about spectral synthesis, but real space-resolved spectral synthesis. Because perhaps the space resolution, or the spatial resolution, will allow us to break degeneracies, just like this allows the degeneracies to be breaking in the music analysis field. Okay, basically this is the presentation. I still have a few more minutes, so I'm passing to a different thing that it's called compressed sensing. So we all know these beautiful instruments like Muse, like this IFUs, like Muse, that they have a superb resolution of 300 by 300 pixels in terms of spatial resolution. It happens that with compressed sensing, we don't need actually to use a brute force approach like Muse is using and other IFUs are using. So if you're using this compressed sensing approach, since 2007, so this was the first compressed sensing hyperspectral camera, and those are two more modern hyperspectral cameras. With something with this size, that is this size, you can have a spectrograph that has the spatial resolution of your detector. So if you have a 4K detector, it will be a 4K spatially resolved IFU. It's just that here, the software also makes an integral, the software will become an integral part of the instrument. There is basically no separation between software and hardware here. I'll just give an example of an observation performed with this camera that was built by Hall in 2014. So if we just put if we just point to this camera, to a scene, this is what you will read in the detector. So basically, you can see that there are many specs completely overlapped. It's a mess. Basically, when you write the sparse reconstruction problem, what you do is to have a novel complete dictionary and no sparse coefficients. These are the projections, so these are the coded projections that you use just like we used in a certain way in the X-ray observations some years ago. And this is the sensory image. And what we're going to try to do is to solve this problem. Basically, to find what are the unknown sparse coefficients that will allow you to reproduce the sensory image. And this is, and everything is done in the N1, as I was commenting earlier in this presentation. So after you perform this optimization and recover the image, you can produce, for instance, the synthetic RGB image, or many images in any wavelengths that were covered by your rating or by your rating. This is just a group construction for 420 nanometers. And this is just showing reconstructions for 3 parts of this tube. So this is a color reference tube. And so the line showing the ground truth is the pointed line, the dotted line. And the through line, the continuous line, it's what you measure from the reconstruction. It's for the reconstruction for each different wavelength. So this is really amazing. So if you imagine that you can use this for astronomy, futures may become obsolete in a few decades. I don't know if this is happening or not, but if this technology, because this technology is it's very young, so perhaps we will find some problems that are impossible to solve, but perhaps not. Anyway, some opportunities for interesting works. The fundamental issue in the spectra in the certain way, as we recommended, is that they just contain too much information for our brains to process. So we need to find ways to better explore the information that it contains there. And three of these ways that can help us, that can help humans to extract information from spectra are the machine learning methods that have been covered a lot in this conference, the dictionary learning method that I just commented, and another method that's called causal inference that I will not comment, but if anyone wants to discuss a bit, we can discuss later. But causal inference, basically, it comes to break that assumption that we did that correlation is not causation, that's true. But causation implies correlation. So in many cases, from the correlation, you can extract causation. And there are many methods in the computer science words that are appearing. Most of them were published after 2014 to solve this causal inference problem. Okay, thank you very much.
Thank you for your interesting talk. And can I know, please?
It's more comments. I'm really pessimistic about this stuff, this reconstruction stuff. The main lesson we learned from the HST that was launched with bad optics and then fixed is that image reconstruction techniques do not work. There were dozens of these developed in early 90s by people who were trying to reconstruct images, and then they re-imaged the same thing with PIC2, and nobody is talking about the fact that they've never seen in WIFIC2 what they reconstructed using those techniques. Those techniques work perfectly with zero background, like in very simple sense. So your dictionary learning, your dictionary has to be finite. Right now, either you, in astronomy, we're trying to learn something, well, in the ideal world, something new that is not in the dictionary. So if this something new is not in the dictionary,
Your dictionary learning does not assume that you know the dictionary. The dictionary learning techniques, that's why the name is dictionary learning. It will create the dictionary. From the data, from different sets of data, it will try to create the dictionary. This, just show you. Sorry. Where is the other? Okay, so basically, this is just one possible algorithm for performing dictionary learning, right? Basically, you initialize your basis vector to random values, and then you go updating this basis vector. You change at each iteration. You change it, and you try to learn the dictionary. That's the point of dictionary learning.
no, because for the sparse data, like an X-ray where you have no background,
That's
the
it.
things that you showed in one of the last slides with this hyperspectral stuff,
Yeah.
it's been in place for a decade.
No.
Because in X-ray, they can recover the energy of every photon. Well, it's not the same algorithm, obviously, but
You
basically,
didn't have it, no,
in X-ray, you have the mask, you can encode the image.
yes, exactly. But you didn't have the N1 optimization tools that you have now. All the mathematics that allow us to do this today were developed after 2006. It's not the same thing. It's similar,
It's similar.
but it's not the same thing.
I'm not talking about the same mathematics. It's just
Earlier on in your talk, you showed you rather made this video clip, audio clip, and then 3 separate audio clips. So if I understand correctly, for those 3 ones, you had 3 different filters, which was taking out the sound or the music.
Yeah,
So it's just a question of filtering it out.
No, it's not a filter. It's not a filter. Basically, it's what was happening there. It was trying to create a matrix. You're trying to create the data that looks similar to the data that you're hearing. So the computer is trying to decompose the signal using some constraints. And the constraint is that you can model this using Gaussians. So in the spectral domain, you can model using Gaussians. So you have very long, very big Gaussian matrix.
So this is just like it is scanning a Gaussian around, and then it just picks up certain things which are making sense.
No, it's not that. It's really trying to solve an optimization problem. It's not scanning anything.
How can you assure that the reconstruction has a physical meaning? I mean, for example, PCA.
Like,
We can take a data set and we apply PCA and we recover, say, 3 components. These 3 components may or may not have a physical sense.
no, that's completely true. And actually, this paper, in this paper, they show the PCA decomposition and this decomposition. And they show that in the PCA decomposition, only the first principal component has a physical meaning. But all the other PCs are completely unphysical. And here you can assure, you can never assure. That's the tricky part of supervised methods. You can never assure. You need to look to the result of the method and try to interpret it. But that is on you. That is on the human. At least today is still on the human. Right? And just in this example, they had a normal spectrograph, and then you could compare with the ground truth. So the ground truth is the blue, and the red is the learned. That's the learned by himself. Using that algorithm chosen randomly and optimizing using CG methods, so conjugated random methods. The G norm.
I thought you challenged me to respond about the saving of data. I'm not going to refer to it later, so I can do so now very quickly. Just to say, yes, it is true, we do have data which astronomers bless them have kept safely in good condition with decades and years, centuries, more than a century. And some people are trying to digitize them for the benefits of all our colleagues and for posterity. The difficulty that we face is a kind of sneering attitude from our peers and from younger people who say, who wants the old stuff? We have new stuff, so much better. Totally losing sight of the fact that you cannot, if you are reading for electronic archives, you cannot go back beyond 25 years, we can go back 125 years. And so, if you can help, you can help by persuading people, telling people, educating people, that those data purport in quality in some way, and nevertheless essential for any kind of time domain.
Yeah. Thank you.
Anybody want to ask questions? Okay, let's move to the next one. Our next speaker is Adam, but today he's not coming, so we will make it by remote video. And this talk title is the curation model for toolkit, which we call the SLAT.
If you can avoid using the internet so much now, so we can be sure this is going to work.
Hello, Adam. Can you hear us?
Yeah, I can hear you, okay. Can you hear me? Great. Okay, so you can see me as well. Hello. Okay, I'm just curious. Okay, so I want to, first of all, thank Colin and organizers for allowing me to give a talk. Remotely is not the ideal situation. Unfortunately, we have these issues here in the US lately, as you probably know. So I wanted to talk a little bit about the project that we're doing, which is not quite as big data as some of the big data talks that have been shared so far. This is in comparison kind of small data. But the idea is more to think about the spectral libraries that we're building, not just in the sense of sharing the data out in whatever formats they are, but also how do we curate the data? How do we give extra information, extra resources for those data to actually be used? So this is a project called SPLAT, which stands for the Spectral Libraries Analysis Toolkit. This is based on data obtained with the IRTX instrument, and primarily for very low mass stars and brown dwarfs, things that are MLO and dwarfs inspected. This is small for a couple of reasons. For one thing, the current library only has about 1,500 spectra, so in many ways it's not big data in any way. It's also much lower resolution than some of the speculated sets that have been discussed in the meeting so far. These are resolution typically about 100, going from 0.8 to 2 microns. So very specialized and low resolution set. It's required to be that low resolution primarily because of very faint magnitudes in these sources. So we currently have a library that is online, and this can be accessed by the URL you see on the page there. If you go to that page, you will see something that looks like this, which is just your standard sort of very old HTML table of information where you can download individual files, you can look at individual files as plots. You can also grab just the archives of the various sort of subsections of the data that are in here. And this has been very useful for the community. It's been cited over 120 times in literature in the last 10 years. And so I think it's a valuable resource for the guys. But it's also been very limited. And part of that is just how do we maintain these data portals, particularly when we may not actually have any funding or support to do so. And so the site that you just saw was essentially a static site, about a decade old at this point. As a result, you're not really able to search through the sources or filter them in any way. Data itself is difficult to maintain and update, particularly the data on the sources themselves, because they're continually being observed. New information about their distances and rate of losses, for example, are hard to incorporate into the data set on a dynamic basis. And as a result, because of timing, usually the updates are infrequent and they're done. Once we're done, once we're finished for a long time. So currently the website is about 5 years out of date. And so that's again part of the resource management. How do we actually get enough time to maintain this information site? How you can treat data in the library is not that straightforward. Mostly people just send me spectra and I try to get them up whenever I can. There's also no integration with the virtual observatory frameworks, and there's really no analysis tools as well. So this is really just a set of resources for those who are expert enough to know what to do with spectra. So when I think about how we use our spectral libraries, I'd like to think in these two axes. One of the accessibility, how widely available, how easy it is to get the data, and also utility. And so if you think about where this progresses on both axes, as you have a more accessible, more utilitarian library, you increase the number of users, which therefore increases the number of potential publications, and also the number of citations. And so it's a much more productive site. So most of us have data sets that are kind of down here at the low end, which are accessible to one or a few, and useful to one or a few, and that's our private data sets, which we just collect from the telescope and store on our exabyte drive we no longer read. And of course, more increasingly, what this library, this meeting is about is the kind of public archives where the data are totally accessible. We can download online or from various resources. But generally, the data is restricted to just the data. So there may be some metadata associated with the spectra. It's typically what the data is bits files or some other format, which is associated with the data themselves. And because of that, users, particularly new users, may not be able to know how to access the data, how to use them in the first place. It will require some expertise and training. So while it's very high in accessibility, it's not necessarily that high on the utility level. So I want to promote sort of a model of curation, which is where the case where you have full access to data, but you also have access to the tools. And so you can really jump into doing some data analysis. Even students can jump into doing data analysis quite quickly. So I put a definition for curation up on the screen there. But basically the idea is that going beyond data, and this is kind of what the last speaker was talking about as well, is going beyond the data and thinking about how we can actually better use of the information in a more widely accessible way. So this is built on some innovations that have happened in our community over the last few years. One of those is the open code development innovation, work done for developing AstroPi, dot astronomy. Many of our meetings now have hack sessions to develop code collaboratively. All of this has put a lot of collaborative work into developing the same common tools that everyone can use together. And so a lot of the platform I showed today is built largely on the AstroPi library, with several additions that are specific to the data set themselves. But it wouldn't have been possible without these collaborative program tools. So we now transitioned this resource from the specs library to the specs library analysis toolkit. And of course, we have a logo transition at the same time. And the goals of this were to create an online resource that can both service specs data, but also provide analysis tools that can be used both by expert and amateur researchers alike. So we want to make sure that the tools that are developed in an intuitive way that really matches the specs data set, matches the data as closely as possible. And then also to standardize and expand that spectral data volume, so going from the 1500 up to much larger numbers, but doing it in such a way where the data themselves are fairly uniform across the different frameworks. And then finally, to make sure that the data is DO compliant, so we can take advantage of online resources and reduce the need of having locally stored data. And so we don't have to update the source data all the time if we have a way of accessing the data. And that's something that we don't have to maintain. Now, the other element of this was that it was a fundamentally student-centered design project, and it was focused on having the students both learn the process of analyzing spectral data, but also build the tools that they need to do the analysis, and those tools then get implemented into the code. So this has been developed over the last 2 years, primarily by undergraduates, by about a dozen undergraduates that have come through my lab over this time. And they've been done through a series of basically challenge exercises. So I would start them off very early on as just a simple exercise, like just plot the data, show me a picture of what the data looks like. And that was sort of one of the building blocks for visualizing what the data looked like. Then it gets progressively harder as we can build on this. So by the fourth exercise, they were starting to compare the spectral models and figure out how to optimize those comparisons, how to use different statistics, and actually visualize those results. And then as we got further along, we realized that we have enough stuff that we can start really having to visualize many different aspects of the data. So that we can make flat, pretty exercise for one quarter. And all of these exercises were folded into the code, which now spans about 10 different modules that contain somewhere around 100 different programs, about 9,000 lines of code. And it also is matched up to about 2,500 spectra now and about 8,000 spectral models. And so it's a fairly comprehensive set that provides not just the raw data, or at least the empirical data, but also all the tools you need to analyze it. So just to give some statistics of where the data set is. So right now we're at about 2,600 spectra, give or take, about 2,300 sources, from about 80 different citations, plus a whole bunch of stuff that hasn't been published yet. Now again, that may not seem like big data, but, and I should say most of these, about 90% of these are very low mass dwarfs, because that's kind of the scientific focus of my group. But there's also about 10% of these sources that include main sequence stars, carbon stars, giants, white dwarfs, and galaxies, a couple supernovae. Saturn is in there because we had a really bad night one night, so we can look at Saturn. Now, it seems like a small data set, but this is about 96% of the variable mass dwarfs that I can look at within 25 parsecs. And so even though it's not millions of spectra, it is a fairly complete sample of the sources that are nearby the sun, at least for the variable mass dwarfs. And so these plots show the distribution of the spectral type on a log scale. Obviously, we're dominated by ML dwarfs because they're brighter, but you can still see we have hundreds of T-dwarfs in the spectral database. And then you can also hopefully see the distribution of the sources on the sky is pretty uniform except for the galactic plane. Now, there's a whole set of different analysis tools that are in here. This is just a list. What I wanted to actually try to do is give a quick demonstration of how Splatter is used. And so let me see if I can switch over to another window. So those of you who are familiar with Python may know this as a Jupyter notebook, but this is just going to demonstrate some of the code. Can everyone see the code there? Okay. So just like any other, so if you're familiar with Python, this will look fairly familiar. If you're not familiar with Python, don't worry. Trying to serve the basics of what happens. With every code, we just import the package, which is called flat. And then data are just accessed by a series of commands where you can search the library. So one very common one is just to get a spectrum. And in this case, get a spectrum that is indicated by the short name. So just the sort of four numbers of RNA in that. And so I can grab that, it search the library, finds it, and puts it into a variable. And I can then show some information about that object. So it tells me the name, when it was observed, and also the citations for the classification, but also where it has actually been stored before. It has built-in visualization tools, so I can actually just plot the spectrum pretty quickly by just saying plot. So as you can see, we've got a keyword here. And then there's other ways to display the spectrum that are more fancy. So here's another place so you can plot it, so you can actually see the various labels for the molecular features that are present in the spectrum. It's got all sorts of tools to manipulate the spectrum. So for example, if I wanted to flux calibrate the spectrum, I can flux calibrate it to with 2 mass J magnitude of 15.4, and I will assume that it's the absolute magnitude for the source. So I can do that and plot it. You can see now that the scale has changed, so that we're looking at absolute flux units. And I can also convert between different flux units as well. So this is the same spectrum, but now in F nu as opposed to F lambda. There's also empirical tools to classify the spectra based on indices, but also comparison to standards. So this particular tool here reads in all of the spectral standards that have been published between M0 and T9, and then goes through and tries to find the best comparison between those just by single comparison. It takes a little time to reading all the models. But once it's finished that, a plot will come up here that will show the best fit spectral type. Hopefully. There we go. All right, so our original spectrum is in black, the standard, which is the T7, is in red, and it can show also the difference in spectrum there. So the very efficient way of getting out the spectral classification is, of course, just by comparison. There's a number of empirical relations that are stored in here. So, for example, if I want to know what the effective temperature is for a T7 dwarf based on the Philip-Cosby et al. 2015 scale, there's a number of these scale leaders that goes, so you can just find that number out. And then, as I mentioned, there are spectral models that are also contained here. So, for example, if I wanted to read in an 800 Kelvin log G of 4.5 BT settle model, well, I can just use that using this Git model code, and I can plot that up, and you can see there's the same kind of spectrum. And it's smoothed at the resolution of the specs data. It's defined smoothly for that. And then we can also look at some tools to compare the spectrum and see how good it is. And this is comparing the spectrum between the observed data and the model, scaling the model to the optimal scaling, and then plotting that. And you can see that happens pretty quickly. You can see that's what the comparison looks like. So there's a number of tools that will do this more automatically, so you can search through the grid as opposed to just going one model at a time. There's also an MC fitting code that will do this, so we get distribution of parameters as well. Okay, we'll go back to the slides.
Okay.
Sorry, can you hear me?
Yeah.
Okay.
Yes.
Okay, so this is the summary of all the tools. I don't have time to go through all of them. What I wanted to highlight is just a couple of science cases that have been used for this. And so we've been recently using this book database to analyze the host stars of exoplanet systems. So one in particular is TRAPPIST-1, which is this great system that has somewhere between 3 and 4 planets and potentially more around it. The star in question is an M8 dwarf, so it fits into our spectrotype range. So we've used a number of these flat tools to both get a more accurate classification, fit models to the spectrum, and even analyze the high resolution data to look at helicity signatures in the spectrum. So there's tools for that as well. A number of students who have been building this code have had specific science investigations. So one of my former students, Mike Lopez, who's now a grad student at Ohio State, was able to discover that a formally classified giant star is in fact a young member of a 24 million year old cluster. And that's the 32 Orionis cluster, which is the first ground dwarf we found in that cluster. And its effective temperature is sort of at the ground dwarf planetary mass regime. Now, this was missed in the previous data because there wasn't really the tools to compare it to young sources. Because we have literally hundreds of young brown dwarfs in our sample, we can actually find much better matches than just looking at specific features. My graduate student, Danielle Yufi, has been using SPLAT to do population synthesis. So I'm there's been some talks on galaxy population synthesis. This is kind of baby population synthesis because there's only two sources, binary system. But there's still enough variation in the spectral shape of these two sources that you can actually get out some very detailed parameters of the components themselves. So we see in the upper right corner is a combination of two individual spectra from SPLAT, one is an L dwarf, one is a P dwarf, and those added together give the spectrum resource in question. And we've since been able to verify that this thing is an RV variable with a period of about 2 years. We're also comparing against other different data sets, and so these are data from the from IWSSL2017. These are parallel fields where they just happen to stumble across some ML keywords that just happen to be in field of view. And so another one of my graduate students, Christian Aganze, has been able to classify these sources and discover basically how far away they are. So these are ground dwarfs that are kiloparsec scales, and so they're really starting to probe much more deeply than we can do with local surveys like TMAS. But another example is we've been also looking at apogee spectra as a separate project, but the SPLAT data are also useful for providing some context. And so while apogee provides very high resolution over a very narrow range, which is indicated by the yellow band in the spectrum, we're able to look at the entire infrared spectrum and sort of compare the models that you would fit from the broad spectral range as compared to a narrow spectral range. And others have been using this as well to do things like test retrieval models. These are some plots from Microline, where they've been using the data to test the retrieval modeling programs, in which they're able to actually model out the pressure temperature profiles and different abundances. And my colleague from the Quantum faculty has been using these spectra to fit exoplanet spectra that have been directly imaged from instruments such as G5. Many of the direct exoplanet high contrast imagers have basically the same resolution as we have for the SPLAT data. So they're actually quite well matched to comparing against exoplanet spectra. And surprisingly, there's even an exoplanet extragalactic interest, mostly to get rid of the brown dwarfs in their samples. The folks have been using the sample photometric components of the library to identify spaces in various parameter spaces to exclude brown dwarfs as compared to, say, hydrogen cal. There's also been an education component of this project where we've been developing resources to introduce school kids to spectral classification, which sounds like a very dry subject, but in fact, there are ways to make it fun, and we have lots of little puzzle pieces to put together. And so we've been developing some tools from that base in the library. And we've even had some artwork that's been developed as a result of the library as well. So we've been trying to make this as sort of multidisciplinary and cross-disciplinary as possible. So we received some funding to develop this library, and we're going to be continuing that over the next couple of years. We are, for example, starting to work with Enrique Solano and his team at IWSSL to develop a virtual observatory framework for SPLAT. That's going to happen through the Spanish Virtual Observatory. This is a mock form that might be used to search for the library. And then you can use other VAO tools, spectral analysis, syntheses, equivalent measurements based on those spectra as well. And we've also been designing some special purpose tools. So for example, I'm working with the Euclid team, and specifically the ground up independent latency scientists team, to make some predictions about what the ground up spectrum will look like if they will get with Euclid at various distances and magnitudes, and what we can do in terms of the accuracy of classification of those sources. And then finally, what we'd like to do is start expanding this out beyond just the very low mass dwarfs. And so we're starting to look at other source types such as asteroids, expected to use a lot for asteroids, but also galaxies and familiar stars. We've been starting to build a framework for building in additional instrumentation usage. And so we have some hooks in for using this for specs SXD. For fire, which I was really happy to see that the fire spectral library started to be developed. But then it's something you possibly rate our code as well. And we're also been working with the IRTF directors to start getting out some of the published and unpublished spectra that are contained in sort of 12 to 15 years of the specs observations. Unfortunately, we have a couple of observers who use specs that don't contribute to it, so we're trying to figure out ways we can get that data shared out. So you can, if you're interested, you can definitely help. We're happy to get field testing of the code as it is. It's available on GitHub now. It is not 100% bug free, so we are happy to get some directions on how to switch some of those bugs. We'd also like to know from the community what kind of tools you'd like to use. We can build those tools into the library if possible. And of course, we hope that the resource is useful for your research. So we want to encourage you to use both the data and the tools to do whatever research you want. And now I'm there. Thank you very much.
Thank you, Anna. Any questions, please?
A very trivial question, but for this current generation, people will prefer to click rather than typing all these kind of things. It's very complicated and fairly not obvious what people should type. It's like GUI or so that can be used.
So Paul, would you mind just repeating the question?
The question is basically.
Was, little codes that you have to put in there to instruct one if there's a version that you click to make the same thing. So IWSSL, so young people nowadays, they want the easiest possible ways to use the tools. And the example you show are space typing items, so you can type the code to get the results. So in IWSSL, if there is, or if you use something like clickable.
No, it's much more. No, it's much stronger than I say. I'm saying that young people nowadays want to click, and if they cannot click, they stop. So, yeah.
They want to click, and they cannot click, they stop.
Got it. I got it. Yeah. So this last summer, we actually had a project to build a web portal for all of the tools. And in fact, it's not that difficult. Once you have the Python framework, there are a couple of basic routines that can connect a web form into a Python code base. And so I had a student actually from Ohio College that was working on that this past summer, and we have some of the calculator types of things. So if you want to figure out what the temperature is, we're getting spectral type or the color. Those things are now are basically ready to go. We're still working on how to do the more calculation intensive things like fitting models or classification. But that's your comment is well taken because I had the same experience on this end as well. So we're trying to build up some web-based platform for the code base, and so customers use that.
I would just like to comment on the name because it's unfortunate that the SPLAT is the same acronym for the similar spectral tools. And basically, we already have this SPLAT as the former Starlink application, which is now being developed as the only code for the spectral handling in virtual observatory. So please, in the future, don't put the SPLAT BO acronym to it. Because as far as the classes, SPLAT dot something and so on will be confusing.
No.
So Peter is saying that we found that it was unfortunately the choice of the name. It's not the job that is already
It's an application.
It's an application developed originally by Starlink people, and now it is being developed as a continuation of it under the name SPLAT/VO.
So application developed by Starlink was also called the SPLAT, using the SPLAT-VO. So it just has you want to add VO in your name so that things don't get too messy.
Fair enough. Yeah. Unfortunately, I was very aware of SPLAT beforehand, the Starlink SPLAT code beforehand, and I tried my best to come up with an acronym that was also something that I could say as a word, like split it or SPLAT, and it just wasn't creative enough. So I try not to use VO.
Any questions? Any more? Okay, let's thank Adam again. And let's invite Gisbert to give us a talk about e-commerce as well as libraries.
The audio working?
Yes.
My talk has been shifted around. It started off on Tuesday, then it got to Thursday morning, then to Thursday afternoon. And I must say I'm not happy about that, because although with respect there are some great talks coming tomorrow, I have nevertheless been able to hear a great deal of what's been going on. So I can, in a sense, summarise in my mind what you're all about, and then add a few things which rather surprisingly cannot come up. And the particular thing which I was going to talk about anyway, which has not come up, is this matter of describing what you're presenting to people in your libraries in words that are accurate and true. It is very, very tempting to present something like a library and to another person who will then pick it up and say, this is done, we know this. And it will not necessarily explain where there is, where the entries have come from, their provenance. It will not necessarily explain adequately enough whether they are first generation information bits or second generation, and so they've been copied from one publication to another. And in so doing, they will be taken out of context. And in view of what you're doing, that's actually very important to sort out. Now, at some stage, I think on Monday, Rainier mentioned, in a sense, a guess, that continuing along the line of that sort of particular argument at the time, there was a lot of sociology involved. There is a lot of sociology involved because you're dealing with people and with the way people treat not their own work, but also that work of other people. And also, there's another sociological factor which cannot be ignored, is that is the effect, the magnetic effect, the disastrous effect of publishing something. Think of the whole of the people in the pub arguing. I have friends they're arguing and they're scribbling on backs of envelopes and more likely on backs of beer mats. And they will come up with all sorts of theories and results, but they're only on the back of a beer mat. And something like that would be thrown in the bin. Take that same back of the beer mat and turn it into paper and publish it. And immediately it changes to a whole new status. It becomes truth, it becomes proven fact, it becomes something that you teach other people. And that goes through the whole process, the simple process of putting it into print. And what you're doing with brokers is that same action of putting something into print. So there is a great responsibility on your part to ensure that what other people are able to take from you as your best opinionated result is in fact well explained in terms of the errors, the sources, and in particular where those sources came from and what were the errors associated with those sources. I was fascinated by the photography talking about desire benchmark stars until she got to the point where she said that the effective temperatures they come from the literature. There's this awful author called the literature who publishes everything and everything. And if you're not careful, you'll be mixing in a very heterogeneous way bits of information, results that come from totally different sources and totally different kinds of analyses. And unless they're really homogeneous, then if you absorb those kinds of interest and analysis, you are adding in possibly systematic errors whose measure you cannot define. And so it is it's important to you as the author of that library to ensure that everything you bring in is homogeneous in the way to understand. And it is responsible on your part to ensure that the people who use that can understand and can assimilate the errors that have been incorporated. Otherwise, you're going to build in systematic errors into some parts, other systematic errors into other parts, and it will downgrade the quality of what you're otherwise doing. I'm not saying that everybody does this, but it is very much a danger, and so often this week, I've read that people have been taking results from the literature, and the literature is a very, very heterogeneous source. And so often, people find comfort in numbers, and I mean that in two ways. They like to, if three people have produced a number, and two agree, so it can't agree spot on, and the third one is outlier. The order of the third one will probably want to choose the two who happen to agree. Because somehow, if somebody else has put into this magical thing called print, a number, and yours is like it, you therefore think, that must be right. It is fine. You're a bit scared to stick out and say, no, I think it's different. Quite often people do tend, for reasons that they can't quantify, to go for the comfort zone, which is being like other people. And that's dangerous. I had a comment on Monday or Tuesday, that we know that most early type stars are binary. I don't remember who named it. And I wanted, thank you, I wanted to take a card and say, where's the proof? Because the only source I know that sort of information is again the literature, and mostly in the form of the Bright Star Catalogue, which brings you 10,000 stars and has brought together out of the literature their spectrotypes and amongst other things their radio velocities. If the velocities published in the literature are sufficiently disparate, then the catalogue will say the query, meaning variable, is a variable star. And you'll find that most of the O stars and B stars are written down in that catalogue as variable. The reason is that most of the velocities, if you look up in the literature, you'll find most of the velocities of those stars are measured on photographic plates. And when you've got a variable, because the star is rotating, the pictures that you're measuring are very broad, and it's just unavoidable that you will get a lot of scatter in the results that you get by trying to put a crossbar on a line that is very short. And so there's a scatter was enough to tell somebody else, oh, this star is probably very good. I had a first-hand example of this when a few years ago I was working on lambda blue stars, which is one of my favourite topics, along with Chris Crawley and Richard Gray, both of them are experts in classifying those stars. And they asked me to follow up a suggestion made by a French and an Italian authors, which was that lambda blue stars, which are A-type stars, they tend to have broad lines and very low metallicities, and their source and their explanation is just puzzling. And the suggestion that they was that these stars are actually composite double stars, square composite spectrum double stars, which happen to be they've not been measured properly and they've not been recognized to be double stars. And the challenge to me was, can you take their samples 20 that they suggest are very strong candidates, and measure them and the observers and get their spectra from the observatory, I did select 12 stars, and of those 12, 11 in the recording of white star particle, variable velocity. It took me 5 years to show that that was wrong, because I had to measure, I had to look at variability on time scale, 1 day, 2 days, a week, a year, 5 years, something like that. And so I took, overall it did take me 5 years to get that thing. And of the 12, of the 11 that they had been variable, none of them was variable. They're absolutely spot one on top of the other. The velocity corrected spectrum, absolutely no signal whatever for variability. When you really do it systematically and carefully. One star, which I did not say was variable, was in fact a spotted star. And it had its sunlight profiles all over the place because it was rotating every 15 hours. And so it was an awful mess. But so that was actually a new discovery. It's only third time we should know the discovery before it's really sorted stuff. But that brought home very much the time wasted by careless comments such as these stars are all variable because we can play with scatter velocity. And in fact they are not. Because in a sense it was wasted time with the value of having a wasted great wasted. And as I've already mentioned, the Gaia benchmark stars. Although most of the libraries workings that you're doing are much fainter at lower resolution than the kind of things that the Gaia benchmark stars are being used for. Nevertheless, we've got to start and get the fundamentals straight, as right as possible. And so the analyses of those Gaia benchmark stars have got to be as good as absolutely possible. And one thing that people tend to skip over is this full attention to the instrumental profile. Let's talk about the PSF, the point spec function, and do by some kind of appropriate calcium, which will blur the spectrum according to appropriately. Now, if we can think what an instrumental profile, how it's formed, and how it really is constructed, it is formed by scattering of light from the grating itself. And the grating will have ghosts, and the grating will have winds. And in 1969, the instrumental profile of Nautilus 102 which can be used better up into the fourth order lines. That grating, the instrumental profile was examined extremely carefully. My then husband and I, we stuck a laser, which was then part of the top. We stuck a laser in the polar axis of that telescope and photographed it a number of different exposures and built up in a mosaic way in units of great intensity what the profile looked like to the extent that we could follow the winds to an intensity of 1 million, 1 times 10 to the -6 of the peak profile. And while most of the energy was concentrated in the middle, it was enough, and a significant enough, that in effect, we lost 5% of every group that we measured. And it wasn't just a question of saying, well, we can see where the light goes, because in absorption, for absorption, you do not know where the lines go off to infinity, and you cannot reconstruct where it's gone, because that absorption, the absorption is lost. If it's emission, you can see where it's gone, you can then rebuild it and put it back to where it used to be. With absorption, you can't. You can only make some kind of averaging analysis for it. And if that's not done properly, and it's in fact rarely done really well, then all the equivalent bits to be measured for the dimensional stars and any kind of analysis is in that measurement equivalent. They're all going to be systematically wrong in a way that can be corrected, but probably has to be, or maybe corrected differently by different people's numbers and the heterogeneity that I'm complaining about. And this is, again, something that needs to be watched very carefully. It can be treated, but it can never be restored. We heard this afternoon about reconstructing it. You can never reconstruct something with an absorption feature. It's a really visual in that way, because the information is gone. It's not a question of being able to find it. It's not there anymore. It simply isn't. The other point that I would like us to refer to, my unit was social working work, is that several people have talked about using synthetic templates for newer styles. I want to turn it around the way. But which came first, the synthetic spectrum or the real star? And I think we need to remember, and this is something we need to go back to remember, why it is that we've got to look at that. The stars are the right thing. The templates and the synthetic spectrum are only what we can recreate to try and match them. That doesn't go backwards. The information goes only in one direction. Or it doesn't come in the text we were showing yesterday. I'd love to write a paper on the vulnerability of theoreticians, but I don't think in German would accept it. I did have a very interesting example of the point I could make. I was working with a catalog a very well-known theoretician of evolutionary models of double stars. And he'd taken a lot of the results that I had had from a work I did on quantum spectrum and had a sample of 45 stars. He'd taken the results that I had allowed him to use and passed them through his model of their evolutionary status, and had concluded that he could now reconstruct the stars as they looked to be. And he was effectively writing in a table in which he gave the improved parameters for those stars. Not the ones that I observed, but the improved ones, because the theoreticians are always right. I refuse to be called from that. I could not, as an observer, say, I believe my observations are wrong and the theory is right. I couldn't work that way. And so we do have to be careful which tail, how the tail may go the job in this case. And I think, though you've got some wonderful examples of matching spectrum with templates work, do get the essence the long way around. Because what you do will then influence the users who use the products that you're producing. I don't think I really want to go any longer because we're running out of time a bit, so it's nearly not possible. But I do want to make this point that, and I haven't heard this so far in the meeting, to identify carefully what is objective and what we do, what comes from absolutely first-hand spectrum, and what is subject, what is the information that you have deduced from what we do. And to get those clear, because your users will not know. If you don't put in some ways into your catalogs or your labels, your users will never know. And they will come back to you and say, we know that this star is an A5 star, or this is a typical K giant because your catalog says so. And that may not be true. I was at a meeting last November of the nuclear scientists who were grappling with the problem of what they call knowledge management. What they meant was information management. Everything that they talked about, everything they wrote, had this dual letters KM. But the knowledge management, every department had its own KM problems. I get what similar to this, but you're not really dealing with knowledge. Knowledge is something that's a higher echelon of what you have got out of your information. You're really talking about information management. So I have to say that at the end of the week, some people were actually talking about IW rather than KW. So I got somewhere. But I did have to make the point, I had to make the point on the starting as well. We're talking about information management, not knowledge management. And the wisdom is something way above that is what goes into the thesis or something much more everyday. Anyway, how do I advance this thing? Wearing another hat. Wearing another hat, let me just advertise with other people who are using this medium for advertising. But there is I use symposium on time and astronomy coming up at the end of this year, next November, will be held at Stellenbosch University, which is just outside Cape Town. It's the second one in this, on the theme of time made astronomy. The first one was in 2011, and it was really very successful. And we now feel that 6 years on, we've certainly seen so much difference to instrumentation, to the future, and to the results, that we really must have another one. And so we're looking at this new symposium on the future of big surveys, the future of radio astronomy, because they are right on site. They're right next to SKA and Meerkat, and you've got Salt telescope there. There's a lot going on, which is really hot stuff. So I do encourage you to save the dates. If you're American, you've still got plenty of time to apply for IWSSL platform, and do come along anyway to give us some big after us about our meeting. Thank you.
Thank you, Elizabeth. Any questions, please?
Okay, thanks, Elizabeth, for your thoughts. I just have to comment because you comment a lot about the benchmark, so you comment that. The first thing that you mentioned about the effective temperature, saying like the taking from the literature, maybe I was not very clear in the talk, but this is exactly the point, that in the literature you find such a scatter of abundances and of temperatures in particular, that the good bit was to really start from the beginning and trying to measure angular diameters and volumetric fluxes and getting the temperatures in that way, and making the point that it is homogeneous. It may not be right, of course, this is all work in progress, but it was particularly attacking that point that we should not take the literature as granted because of the same point that you said, that I may just take the literature 1 because I agree with it to show that I'm right, and I'm not going to say anything about literature 2 because I disagree, and that may put me, in something against it.
Thank you. I'm glad you agree.
So the second point that I found really interesting was what you said about instrumental profile, about being very aware of all of this. And this is why, again, in the spectral analysis that we do, we analyze spectra that are coming from different instruments, and we are combining also all these methods so that we can be sure that the results are at least not being affected by these kind of effects. And I think this is also something that in IWSSL is one of the goals of having all these different methods, that we can start thinking how reliable are these kilograms.
5% is quite a lot.
Sorry?
5% difference is quite a lot. 5% correction for 25% is not negligible.
Yes, yes. Yeah.
It's not enough.
Okay, let's thank Elizabeth again. I think we have half a break, and then we have another roundtable discussion.
We will do the same thing again, I guess. Where is Claire? Claire? Are we doing the same thing? Putting the chairs on. People, last chance for you to write your address to get a copy of the IAU proceeding, of the proceedings of the workshop from Lyon. So you have to go on the registration desk now. Tomorrow there will be no registration desk open. Okay?